And let me first start by giving an overview of the talk. I'll start by telling you about what is the positive Grassmannian and what is the amplituhedron. And then I'm going to divide the talk into 3 parts, explaining how we can study the amplituhedron from the point of view of oriented matroids and cluster algebras, as well as tilings and triangulations. And along the way, we'll see connections to various nice objects in combinatorics, including Eulerian numbers, the positive tropical Grassmannian, and subdivisions of the hypersimplex. Okay, so first some background on the Grassmannian and the matroid stratification. So the Grassmannian, GRKN, is the set of all k-dimensional subspaces of an n-dimensional vector space. And I'll represent elements of the Grassmannian by full rank k by n matrices C. And I will generally identify k by n matrices with their row span. So sometimes I'll use C to mean a matrix, and sometimes I'll use it to mean the k-dimensional subspace spanned by the rows. Now, when we talk about the Grassmannian, there's some convenient coordinates on it called Plücker coordinates. So if I is a k-element subset of the numbers 1 through n, then the Plücker coordinate p sub I of C is the minor of the k by k submatrix of C in column set I. And then there's a matroid that's associated to our element of the Grassmannian, and I'm going to identify a matroid with its set of bases. So the matroid M of C is going to be the set of all k-element subsets I, such that the corresponding Plücker coordinate is non-zero. So this is a collection of k-element subsets. These are the bases of the matroid, and I'll often just call it the matroid. So back in 1987, Gelfand, Goreski, McPherson, and Serganova introduced the matroid stratification of the Grassmannian. And so how does that work? Well, if M is a collection of k-element subsets of 1 through n, then we'll let S sub M be the set of elements in the Grassmannian where your Plücker coordinate p sub I of C is non-zero if and only if I belongs in the collection. So we're just partitioning the Grassmannian into subsets based on which Plücker coordinates are non-zero. And so now if this SM is non-empty, then SM is called a matroid stratum. And the matroid stratification is this partition of the Grassmannian into these matroid strata. Okay, so they were studying this in connection with the moment map. So let's let E1 through En be a basis, the standard basis of Rn. And for I, a subset of the numbers 1 through n, we'll let E sub I be the indicator vector of this subset. So it's the 0, 1 vector with 1s exactly in positions capital I. And now the moment map is the map from the Grassmannian into Rn, defined as follows. So C is our k by n matrix representing a point in the Grassmannian. And we're going to map this to a linear combination of E sub i's, these are the indicator vectors, scaled by the Plücker coordinates. And then we're dividing by the sum of the squares of the Plücker coordinates just so that everything lies, just so that all vertices have coordinates between 0 and 1.
To the talk.
So mu of C is going to be a point in Rn, and it's going to be a point with
a girl who
coordinates between zeros and 1. Okay, so now the matroid associated to C is, let's recall, it's the collection of k-element subsets of 1 through n, where p sub I of C is non-zero. Okay, so now given M, a collection of k-element subsets of 1 through n, we can associate 2 objects to M. We can associate the matroid stratum, so it's a subset in the Grassmannian, where your Plücker coordinates are non-zero if and only if I belongs to your collection. But there's also a polytope you can associate to M, which is the convex hull of the indicator vectors E sub I, where I is in our collection. And so Gelfand, Goreski, McPherson, and Serganova used the convexity theorem. This was proved by Atiyah, Gilliman and Sternberg to show that the moment map image of a matroid stratum is the corresponding matroid polytope. Okay, so this is a way to map the matroid stratum in the Grassmannian to a polytope. As a small example, if M is the set of all k element subsets of 1 through n, then the moment map image of the matroid stratum is the convex hull of all indicator vectors of all k element subsets of 1 through n. This polytope is called the hypersimplex. And if k is 2 and n is 4, we just get this, this nice polytope that is combinatorially an octahedron. Okay, so matroid polytopes have many beautiful properties. One notable fact is that they're the 0, 1 polytopes such that every edge is parallel to ei minus ej for some I and j. So the matroid polytopes are very nice. On the other hand, the topology of the matroid strata is terrible. So there's this famous universality theorem of Mignoff saying that the topology of the matroid strata can be as complicated as that of any algebraic variety. Okay, so now I want to say a few words about what happens if you look at the objects we've defined already and put an additional adjective positive everywhere. So the background dates back to Lustig's theory of total positivity for partial flag varieties, also work of Reach around the same time, and then a beautiful 2006 preprint of Postnikov on the totally non-negative or positive Grassmannian. So, so the notation will be GRKN greater than or equal to 0. This is, I'll informally call it the positive Grassmannian, and it's the subset of the real Grassmannian where Plücker coordinates are non-negative for all I. And now, inspired by the matroid stratification, one can partition this positive Grassmannian into pieces based on which Plücker coordinates are strictly positive and which are 0. So now if M is a collection of k element subsets of 1 through n, then we let Sm, T, and n be the set of all elements in the positive Grassmannian, where your Plücker coordinate is strictly positive if and only if I lies in your collection. And in contrast to the terrible topology of matroid strata, Postnikov showed that if this set is non-empty, then it's actually a cell. It's homeomorphic to an open ball, and this gives what he called the positroid cell decomposition. So this has many beautiful combinatorial topological properties, and I'll just say a few things about the combinatorics. So just recall the matroid associated to C is the collection of k element subsets of 1 through n corresponding to non-zero Plücker coordinates, and the matroid polytope is the corresponding convex hull of indicator vectors. And if C is in the positive Grassmannian, we call its matroid a positroid, and we call its matroid polytope a positroid polytope. And these positroid polytopes also have very beautiful properties, connections to, for example, things like non-crossing partitions. And this was studied in an old paper that we wrote with Federico Ardila and Felipe Rincon. For the purpose of this talk, one of the most important things about the positroid cells is that they're in bijection with some nice combinatorial objects. So one of them is decorated permutations on 1 through n with k anti-exceedances. And actually the object I'll talk about most in this talk are some kinds of planar bicolored or Plabic graphs. So Postnikov's theorem says we can describe all of the positroid cells of the positive Grassmannian using these nice combinatorial objects. And so on the next slide, I'm going to explain how to read off a positroid cell from one of these graphs. Okay, so I mentioned the positroid cells are in bijection with Plabic graphs, and these are planar bicolored graphs embedded in a disk with boundary vertices labeled 1 through n and internal vertices colored black or white. And here I have just a very, very simple example. And there's a kind of equivalence relation on the graphs, which allows us to assume without loss of generality that the graph is bipartite and every boundary vertex is incident to a white vertex. Okay, so now, given such a graph, how can I read off a positroid cell? That's what I want to describe. I want to describe how to read off the non-zero Plücker coordinates of the corresponding cell. One can do this very nicely in terms of matchings. So, so M of G is going to be a collection of subsets defined using what are called almost perfect matchings. Okay, so what is an almost perfect matching? I'll illustrate with this picture here. So so I've copied the graph from above 5 times because there are 5 almost perfect matchings, and an almost perfect matching, shown in orange, is a collection of edges such that every internal vertex is incident to exactly one orange edge, and I don't care whether or not the boundary vertices are incident to an orange edge or not. You know, so in this graph here, all internal vertices are incident to exactly one orange edge, and the boundary vertices 1 and 2 are incident to an orange edge, but the boundary vertices 3 and 4 are not. So I would call this collection of orange edges capital P, an almost perfect matching. And then associated to capital P is its del of P, the boundary of P, and that is 1 and 2. It's the boundary vertices touching orange edges. Okay, so there are exactly 5 almost perfect matchings, and the del of P's for these perfect matchings are 1 and 2 for this graph, 1 and 3 for this matching, 1 and 4 for this matching, 2 and 3 for this matching, and 2 and 4 for this matching. And so for G, this graph here, M of G is this collection of 2-element subsets of 1 through 4. And so the claim, the theorem of Postnikov, is that M of G is exactly the set of non-zero Plücker coordinates of some positroid cell, and every cell is obtained in this way. Okay, so the point is we can easily describe all positroid cells using almost perfect matchings of these planar bicolored graphs. Okay, so so now what is the amplituhedron? So this is an object defined in 2013 by physicists Arkani Hamed and Trinka, and it's the image of the positive Ortian Grassmannian under a simple map. So let me explain how that goes. So there's many amplituhedra, and they are indexed by 3 positive numbers n, k, and m, as well as a choice of matrix Z. So we're going to fix positive numbers n, k, and m with k plus m at most n. And then we're going to let Z be a n by k plus m matrix with maximal minors strictly positive. So this is my notation for n by k plus m matrix with maximal minors strictly positive. And now I'm going to use this matrix Z to define a map. And it's a very, very simple map. It's going to be a map from the positive Grassmannian of k-planes and n-space to the Grassmannian of k-planes and k plus m space, and it's simply induced by matrix multiplication. We take a matrix C lying in this positive Grassmannian, and then we multiply C by the matrix Z. That gives us a k by k plus m matrix, and then we take the row span of it. And that, well, it's a lemma, but you can check. The row span of CZ has full rank, and so it represents a point in the Grassmannian of k-planes and k plus m space. And now the amplituhedron is defined to be the image of the positive Grassmannian under this simple map Z tilde. And this is going to be a subset of the Grassmannian of k-planes and k plus m space. Okay, by the way, I'm not so familiar with Teams, so if there's questions, then if you write them in the chat, I probably won't see them. I'm not even sure if there is a chat, but perhaps Francesco can communicate questions to me if there's any.
Sure. Yes.
Okay, thank you. Okay, all right. So that's the amplituhedron. It's the image of the positive Grassmannian under this map induced by our positive matrix Z. And of course, this definition depends on Z, but many of the combinatorial properties of the amplituhedron appear to not depend on Z. The amplituhedron has full dimension k times m inside of the Grassmannian. And when m is 4, its quote-unquote volume is supposed to compute scattering amplitudes in n equals 4 super Yang-Mills theory. This was the motivation for introducing the amplituhedron. And to say just a teeny bit more about it, there's a famous BCFW recurrence for scattering amplitudes that can be reformulated as giving a triangulation of the m equals 4 amplituhedron. And there's been some recent beautiful work of Evan, Zohar, Lacrec, and Tesler proving an instance of this recurrence actually giving a triangulation. So I'll say a tiny bit more about that a bit later. Okay, so the block at the top is just a review of the definition of the amplituhedron. And now, since it's may not be familiar to all of you, I'll just mention a few special cases. So if m is n minus k, well, what that means is that Z is just going to be a square invertible matrix, and so the amplituhedron just recovers the positive Grassmannian. Okay, so that's sort of a boring special case, but anyway, yeah, it shows it in a sense generalizes the positive Grassmannian. Another special case is if k is 1, then the amplituhedron it lies in the Grassmannian of one plane in 1 plus m space. In other words, it lies in projective space, and it is basically the same as a cyclic polytope with n vertices in projective space of dimension m. So let me just say a few words about why that's true. So imagine that m is 2. So then our matrix Z is a n by 3 matrix with maximal minors positive. And let's just denote the rows of this matrix by Z1 through Zn. So each row is just a vector with 3 coordinates. It's just a point in P2. So we have a sequence Z1 through Zn of points in P2. And the positivity of the matrix implies that these points in P2 can be thought of as vertices of a convex polytope in P2. That's what this convex polytope is encoded by the positivity of minors. And then if you think about what's the image of the positive Grassmannian of one plane in 3 space under Z tilde, you'll see that you get the entire polytope. So that's what happens when k is 1 and m is 2. You get a polygon polygon in P2, and more generally for k is 1 and m general, you get a cyclic polytope. Another nice special case is when m is 1. Now your amplituhedron lies in the Grassmannian of k planes in k plus 1 space, which is also projective space. And then your amplituhedron, with a bit of work, you can show it's homeomorphic to the bounded complex of a cyclic hyperplane arrangement. So that's something that we proved with Stephen Karp, and these are some pictures of what it looks like. Okay, so now I want to talk about basically the viewpoint of oriented matroids and the amplituhedron. Okay, so again, I'm trying to put the definition of amplituhedron at the top, just in case people forget. So the amplituhedron is a subset of the Grassmannian of k planes in k plus m space. And the definition is a little indirect, right? It's the image of the positive Grassmannian under some map. And so what would be really nice is to have some good coordinates so that we can talk about the amplituhedron directly inside of this Grassmannian. Okay, so to do that, let's again let Z1 through Zn be the rows of Z, and let's let Y be an element in the Grassmannian of K-planes and K plus M space. So Y is a potential, represents a potential element of the amplituhedron. And yeah, again, I'm going back and forth between Grassmannian elements and matrices. So now if I is an ordered set of M numbers between 1 and N, then we're going to let this notation, angle brackets YZI, which I'll also write as Y ZI1 ... ZIM, this is defined to be the determinant of the following matrix. So what we do is we take our matrix Y is K by K plus M, and underneath it we stack our row vectors from Z, not all the row vectors, but the particular row vectors ZI1 through ZIM. And now what we have is a K plus M by K plus M matrix, and we can take the determinant. Okay, so sometimes I'll refer to it as YZI and sometimes YZI1 through ZIM. So this is called a twistor coordinate. I think it first came up in a paper of Arcani Hamed, Thomas, and Trinka. And these are really coordinates on the amplituhedron. Y is determined by its twistor coordinates. These twistor coordinates can actually be thought of as Plücker coordinates of a related matrix. And so these twistor coordinates are what we want to use as coordinates on our amplituhedron. Okay, and now if we think back to what we did in the matrid stratification of the Grassmannian, we were taking our Grassmannian and subdividing it into pieces based on either signs of Plücker coordinates or whether or not they were non-zero. So we want to do something similar for the amplituhedron. So inspired by that matrid stratification, let's define the amplituhedron sign stratification, where we will now decompose the amplituhedron into pieces based on the signs of the twistor coordinates. So this is something that we looked at with Matteo Parisi and Melissa Sherman Bennett, and in a sense we had looked at this as well for M equals 1 with Stephen Karp. So, okay, so we have this amplituhedron. It lies inside the Grassmannian of K-planes and K plus M space. And for elements on this side, we have these natural twistor coordinates. So now what we want to do is partition the amplituhedron into pieces based on signs of the twistor coordinates. And we'll particularly want to look at the top dimensional pieces. Okay. So, so the number of twistor coordinates is n choose m, right? I have a twistor coordinate for every m element subset of 1 through n. So now given sigma, a sign vector, it's a vector where every component is either plus or minus and it has length n choose m. We'll define the amplituhedron chamber to be the set of all amplituhedron elements whose signs of twistor coordinates exactly agree with this sign vector sigma. Okay, so we're doing something just like the matrid stratification. We're just dividing it into pieces based on signs of our coordinates. And of course, the natural question is, when is a chamber realizable? When is it not empty? In general, for the matrid stratification, many strata are empty, right? Most matroids are not realizable. Okay. Okay, so this is our amplituhedron chamber definition, and we'll say that a sign vector is realizable if I can find a matrix Z such that this subset of the Grassmannian, the subset where the twistor coordinates have the same sign as sigma, is non-empty. And so in general, for general amplituhedra, for general M, it's completely unknown how to classify these chambers. But for M equals 2, we can give a full classification. And something that was very surprising to us was that in this case, the amplituhedron chambers are exactly counted by the Eulerian numbers. the cardinality is equal to the set of all permutations W and S sub n minus 1, where the number of descents of W is K. So there's something very pretty going on here combinatorially. And just to sort of give you a preview of what we'll see in a bit, I'll point out that the volume of the hypersimplex, delta K plus 1 comma n, is the same Eulerian number. And in fact, this coincidence is the shadow of a kind of strange duality between the amplituhedron for m equals 2 and the hypersimplex. Okay. Okay, yes, so that's all I wanted to say about the oriented matroid point of view. And now I want to say a little bit about cluster algebras. And cluster algebras are a very nice class of commutative rings with a combinatorial structure introduced by Fomin and Zalevinsky around 2000. Okay, so let me go back to the amplituhedron for a moment and point out that the amplituhedron lies in the Grassmannian of K planes and K plus M space, and the amplituhedron has full dimension K times M. But this K times M is in general smaller than the dimension of the domain, right? So this map Z tilde, whose image is the amplituhedron, is in general, so it's always surjective, but in general it's not injective. And so in light of that, it's natural to ask, when does Z tilde map a Km dimensional cell of the positive Grassmannian injectively to the amplituhedron? And we'll define a positroid tile to be the image of a cell such that this cell has dimension Km and such that Z tilde is injective on this cell. Okay, so basically we want to understand how the amplituhedron map behaves on the individual cells of the positive Grassmannian, and it's particularly nice to focus on the cells on which the amplituhedron map is injective. So this leads to a very nice cluster adjacency conjecture of Lukowski, Parisi, Spradlin, and Volovich, and it says the following. So let's let Z of S pi be a positroid tile of the amplituhedron, and now this is for m equals 2. So then what their conjecture is about is basically describing the boundaries of these positroid tiles. Right? So these positroid tiles are full dimensional subsets of the amplituhedron, and they were looking at how to describe the facet inequalities of these tiles. So informally, a facet of a positroid tile is going to be a codimension 1 stratum, also of the form Z applied to a positroid cell, and it should be in the boundary of our positroid tile, and the positroid cell of this facet should be contained in the positroid cell of the tile that we're looking at. Okay, so anyway, so we have these positroid tiles, these full dimensional subsets of the amplituhedron, and we want to know about how to describe their facets. And so the conjecture said that all of these facets lie on hypersurfaces described very succinctly in terms of twistor coordinates. They have the form y, zi, zj is 0. Right, and so remember, this is the determinant of the matrix obtained by taking our matrix Y and stacking the row vectors Zi and Zj just below. Okay, so they said facets always lie on these hypersurfaces, and if I take this I and j, and if I just identify Y, Zi, Zj with the Plücker coordinate Pij for G2n, then the set of all Plücker coordinates corresponding to facets form a collection of compatible cluster variables for G2n. Okay. If you don't know much about cluster variables or cluster algebras, then another way to say it is if I look at all of my facets, y, zi, zj, and I take a polygon with vertices labeled 1 through n clockwise, and I put down a diagonal, ij, for each one of these facets, then at the end of the day, I will come up with a collection of diagonals of a polygon which are non-crossing. That's another way to say this. Okay, so anyway, so there the theorem is true, and moreover, this collection of facets won't in general give a full cluster for G2n. Our collection of diagonals won't form a full triangulation of the n-gon. But if we look at any other PHL, any other Plücker coordinate compatible with the collection formed from our facets, then the twistor coordinate YZHCl will have a fixed sign on the positroid tile. Okay, so anyway, so the upshot is that if you look at the facets of a positroid tile, they seem to have very much to do with the cluster structure on the Grassmannian of two planes in n space. Okay, so I'll just make a few remarks on this statement. To prove the theorem, we classified all the positroid tiles for m equals 2. In other words, we classified all of the 2k dimensional cells of the positive Grassmannian on which the amplituhedron map is injective. Another remark is that we believe that there's an analog of this theorem for m bigger than 2, but right now the classification of tiles for m bigger than 2 is unknown. And a final remark is that the theorem suggests there's a cluster algebra structure directly on the positroid tiles, and we can prove this for m equals 2. So I'll just show some pictures now explaining this classification. So first of all, we can describe very succinctly all the positroid tiles for the m equals 2 amplituhedron, and we describe them by explaining the Plaebit graphs of the positroid cells giving rise to those tiles. So how do you do that? So it's a combinatorial algorithm. So to write down an arbitrary positroid tile, what we do is the following. You choose an n-gon, vertices labeled 1 through n, and we choose a bicolored subdivision. And that just means we're choosing we're just choosing a collection of gray polygons inside this n-gon, such that when you triangulate the gray polygons, you get a total of k triangles. And all vertices must be from the boundary of the n-gon. Okay, so this picture over here is what we would call a bicolored subdivision. Now we're going to triangulate it arbitrarily. And then we're going to associate a Plaebit graph. And to associate the Plaebit graph, we put a white vertex inside every gray triangle, and we connect every white vertex to its 3 boundary vertices. And so now what you see in the blue is a Plaebit graph, which gives rise to a 2k dimensional cell of the positive Grassmannian. And the statement is that this is exactly, these are exactly the cells on which the amplituhedron map is injective. And then there's a natural cluster structure that we can put on these cells. And I'm just illustrating it with this picture for those of you who know about cluster algebras, but I won't go into this in any detail. There's a natural way to associate a quiver to our bicolored subdivision, and the cluster variables are going to be proportional to twistor coordinates. Okay, so yeah, so I guess the summary is that when one looks at cells of the positive Grassmannian, so cells on the positive Grassmannian on which the amplituhedron map is injective, then we start to see cluster algebra structures arising. Okay. So now I want to move on to the third part of the talk, and now I want to talk about tilings. of the amplituhedron. So again, this is the review of the definition of the amplituhedron. And as I said before, this amplituhedron map is surjective onto the amplituhedron, but in general not injective. So it would be nice to find a sort of km dimensional cross-section of the positive Grassmannian, which Z tilde maps injectively onto the amplituhedron. Okay, so let me step back and make a more general definition, not necessarily in the context of the amplituhedron. So let's let X just be a cell complex, and we'll let phi from X to another space Y be a continuous surjective map onto Y, and we'd like Y to be a d-dimensional cell complex or maybe a subset of a cell complex. And now we will define a phi-induced tiling of Y to be a collection of closures of images of d-dimensional cells of X. Right. Okay, so we're going to take some d-dimensional cells of X and look at their images under phi. Take the closure, and we want these closures to have the property that phi is injective on all of the cells in X. In other words, this thing is what I would have called before a tile. We also want the union of these things to equal Y. And we also want the interiors of these things to be pairwise disjoint. Okay, so it's going to be a way of partitioning Y into pieces which are coming from appropriate dimensional cells of X. Okay, so there are different ways we could modify or tweak this definition. Maybe we don't care about the injectivity. Maybe we want boundaries of these things to intersect nicely. Anyway, there's a lot of variations of this definition you might potentially want to look at. Perhaps we want to drop the injectivity requirement. Let me just point out that if phi is an affine projection of convex polytopes, then this definition above is exactly Bellera-Sturmfels's notion of a tight phi-induced subdivision. Okay, so this is a reasonable definition which generalizes the notion of phi-induced subdivisions for polytopes. Okay, so now in the context of the amplituhedron, so we do have a cell complex here, and we have our surjective continuous map onto the amplituhedron. And so now a Z-induced tiling of the amplituhedron, which has sometimes been called triangulation in the physics literature, is a collection of closures of images of positroid tiles such that the union equals the amplituhedron and the interiors are pairwise disjoint. Okay, so these kinds of objects, these kinds of ways of decomposing the amplituhedron were first discussed in a paper of Arcani, Hamed, and Trinka, and they conjectured that various collections of BCFW cells give a tiling. For the sort of nicest BCFW collection of cells, this conjecture has been recently proved by Evans, Zohar, Lacrec, and Tesler. So in general, there's this notion of Z-induced tiling, and we have all of these amplituhedra. So let's look at different special cases. And I'm going to show a table here that that gives the cardinalities of the different tilings. Right? We can look at how many pieces, how many tiles it takes to decompose the amplituhedron, and sort of record the sizes of these tilings. And these are numbers that one gets. So, okay, so in some trivial cases, the cardinality of a tiling is just 1. This is when either the amplituhedron is a point or the amplituhedron is the same as the positive Grassmannian. When m is 1, if you look at the cardinality of a tiling of the amplituhedron, you get this nice binomial coefficient. This was from an old paper with Stephen Karp. When m is 2, you get this other related binomial coefficient. And this was observed by Arkani Hamid, Thomas, and Trinka. It was proved by Bao and He, and also sort of studied from a slightly different point of view with this work of Parisi and Sherman Bennett. Now, when m equals 4, you get this nice Neriana number. And this had been pointed out by Arkani Hamid and Trinka, and an instance of this has been proved in this recent paper, Evans-Orr, Lacrec, and Tesler. And now a last special case is when k is 1 and m is even, and then you get this binomial coefficient. And this is the case where A is a cyclic polytope, and this is sort of well-known cardinality of a triangulation. Okay, so we see all of these nice numbers when we start studying cardinalities of tilings of amplituhedra. And there's a conjecture that explains all those numbers that we made with Stephen Karp and Yan Zheng. So let's let m of ABC be this number. This is a beautiful number which counts plane partitions contained in an A by B by C box. And the conjecture is that the cardinality of a tiling of the amplituhedron for general even m is exactly the number of plane partitions contained in a k by n minus k minus m by m over 2 box. Okay, so anyway, so the conjecture is completely open because for general m, there's not even currently a conjecture for how to tile the amplituhedron. But this conjecture is consistent with all of the numbers from this slide. Okay. Okay. So let me say something else really fascinating about tilings of the amplituhedron. And this was a big surprise, which is that tilings of the m equals 2 amplituhedron and tilings of the hypersimplex are related. Okay, so let me just review our notion of tilings in these cases. So on the side of the amplituhedron, we have the positive Grassmannian of k-planes and n-space, and we have our amplituhedron map onto the m equals 2 amplituhedron, which lies in the Grassmannian of k-planes and k+2 space. So this is a 2k dimensional object. And so a z-induced tiling of this amplituhedron will be a collection of closures of images of 2k dimensional cells here, such that z tilde is injective on each of those cells. The union of the pieces in this collection is the amplituhedron, and the interiors of these pieces are pairwise disjoint. Okay, now let's talk about the hypersimplex and the moment map. So here we have the positive Grassmannian of k+1 planes in n-space. Again, this is a cell decomposition. And we have a moment map from this positive Grassmannian of k+1 planes in n-space to the hypersimplex delta k+1, n. And this is a polytope lying inside Rn, and it has dimension n-1. So a mu-induced tiling of this polytope would be a collection of closures of images of n-1 dimensional cells of this Grassmannian, such that mu is injective on each cell. The union of these pieces is the hypersimplex, and the interiors are pairwise disjoint. And by the way, the moment map is mapping positroid cells to polytopes. So each of these pieces here is going to be a positroid polytope. It's a special matroid polytope. And so the conjecture, which we found with Lukowski and Parisi and proved with Parisi and Sherman Bennett, is that the tilings of this amplituhedron are exactly in bijection with the tilings of this hypersimplex. And this is, there's a phone ringing somewhere. So this is
someone should mute themselves.
So this is a strange statement because as this amplituhedron here, first of all, is not a polytope, right? It's a subset of the Grassmannian of k-planes and k+2 space. Meanwhile, this space over here, this is the hypersimplex. This is a polytope, and this has dimension n-1. So, okay, so this is a 2k dimensional non-polytope, and this is an n-1 dimensional polytope. And yet the statement is that the tilings of the amplituhedron are in bijection with the tilings of the hypersimplex. Okay, so I'll give an example on the next slide, but I'll just point out that a corollary of this statement is that the number of fine subdivisions of the hypersimplex delta 2n into positroid polytopes is a Catalan number. Okay, so I want to explain on the next slide a small example of this bijection between tilings. Okay, so let's do really the only example I can draw, which is k is 1 and n is 4. So if k is 1 and n is 4, then on the amplituhedron side, we're looking at the amplituhedron A412. And if you recall, when k is 1 and m is 2, this amplituhedron is a polygon in P2. So this is going to be a quadrilateral in P2. And here tilings are going to be just triangulations. So there are, so this is the amplituhedron, this quadrilateral, and it has two triangulations, this one and this one. And if you sort of get your hands dirty and think about which two-dimensional cells of the positive Grassmannian map onto these triangles, then you arrive at these two Playpick graphs. And then on the other side, the positroid cells giving rise to these two triangles are these two Playpick graphs. And so cells are also in bijection and encoded by permutations. So if you know about that bijection, I've drawn the permutations right here. Okay, so these are the two tilings of the amplituhedron, which in this very special case is just a quadrilateral, and tilings are just triangulations. Now, on the other hand, there are two tilings of the hypersimplex, delta 24, and delta 24 is an octahedron. And if you think about ways of tiling the hypersimplex using positroid polytopes, then you'll see that there's exactly two ways to do so. You can cut it sort of by a plane in the middle like this into this square pyramid and this square pyramid. And on the other side, you can also cut it sort of vertically like this into this square pyramid on the left and the right. These are the two ways of cutting the hypersimplex into positroid polytopes. And if you think about how to get these square pyramids as images of positroid cells under the moment map, then you arrive at these two Playpick graphs. So yeah, if you recall, we can read off the non-zero Plücker coordinates of a positroid cell using the almost perfect matchings of a graph. And so I claim that if you write down the almost perfect matchings associated to this graph, then we will get precisely 1, 2, 2, 3, 1, 3, 2, 4, and 1, 4. We'll get all of the two element subsets except for 3 and 4 as the boundaries associated to the perfect matchings. Okay, so this graph maps to this square pyramid, and this graph maps to the bottom square pyramid, and this to the left and this to the right. Okay, so there are two tilings of this amplituhedron, and there are two tilings of this hypersimplex. And now how can we biject the cells of these tilings? Right, this was the puzzle that we had to figure out, and we first sort of found the bijection conjecturally in this paper of Lukowski and Parisi. So if you know about permutations attached to labeling positroid cells, then by looking at this example, you should be able to guess what's the map on permutations. 2314 is going to map to 3142, and 3241 is going to map to 2413, and 2431 will map to 4312, and 1342 will map to 3421. And maybe you've already figured it out, but the map is sort of cycling the permutation around. This 1342 to get the permutation down here, you start at 3 and then read 3421, and that's the permutation downstairs. So, so there's a very concise description of this bijection on cells on the level of permutations, and there's also an easy way to see it on the playback graphs as well. So I'll just show what's the map on playback graphs here. But just to step back a moment, in order to relate tilings of the hypersimplex and the amplituhedron, we have to find a map that maps n-1 dimensional cells of this Grassmannian to 2 k-dimensional cells of this Grassmannian, which looks like a weird thing to do, actually. But this is a map which we were calling T-duality, and Pasha Galashin also likes to call shift map, and it's been studied in various papers in the last few years. This was a paper of Galashin, Postakov, and myself. There's another paper of Galashin, and then also Parisi, Sherman Bennett, and myself. And on the level of permutations, we were looking at it with Lukowski and Parisi. Anyway, so there's this interesting map from cells of this Grassmannian to cells of the related Grassmannian, and on the level of playback graphs, you can define it succinctly as follows. G is going to be a playback graph reduced and black trivalent, and the T-dual graph is obtained by this simple combinatorial construction. So I start with my graph at the left, and then for every face of the graph, so every complement of every piece of the complement of the graph, I put a black vertex, which is shown here in blue. Then on top of the black vertices here, I'll put a white vertex. And then for every black vertex of G incident to a face, I'm going to add an edge. So this is a black vertex of the original graph incident to this face, and so I'm going to add an edge. Okay, and then you put in some boundary vertices as well. And so, so the T-duality map, which is the appropriate map on cells, maps this playback graph shown here in black to this playback graph shown here in blue. And so it's this weird, it's this sort of combinatorial map on graphs, which is which maps n-1 dimensional cells of this Grassmannian to 2 k-dimensional cells of this. Okay, so the upshot is that there is a bijection between tilings of the hypersimplex and this amplituhedron. This bijection actually explains the fact that the volume of this hypersimplex is the Eulerian number, and the number of realizable amplituhedra strata of this amplituhedra is the same Eulerian number. So this bijection explains that sort of mystery. And so now I just want to say just a couple words about why we realized there was this strange connection between the amplituhedron and the hypersimplex. And the reason we guessed this connection was that with Lukowski and Parisi, we realized that the F vector of the positive tropical Grassmannian seemed to be enumerating some kind of good subdivisions of this amplituhedron. So basically, a couple years ago, they came to me and they said, we have enumerated some subdivisions of the amplituhedra, we're getting these numbers, and then the numbers they showed me, I recognized as coming from the F vector of the positive tropical Grassmannian. So that was the sort of first clue that something strange and interesting was going on. And then in the process of trying to explain this coincidence, we realized that the F vector of the positive Chappell-Grassmannian was related to positroid subdivisions of the hypersimplex. And then we found this that this shift map or T-duality from cells of this positive Grassmannian to this one seemed to give a bijection between the subdivisions of the hypersimplex and those of the amplituhedron. So anyway, so it was a sort of indirect connection, initially just found as a sort of numerological coincidence. Okay, so so let me just wrap things up by giving a little summary. So the amplituhedron, I hope I've convinced you, is an interesting object, which includes as special cases the positive Grassmannian, cyclic polytopes, and the bounded complex of the cyclic hyperplane arrangement, and also is closely connected to the hypersimplex. And it's useful to study this amplituhedron from the point of view of oriented matroids, cluster algebras, and tilings. And there are many open problems. And so thank you very much for listening. And these are the sort of main references for my talk.
Thank you. So, are there any questions or comments? Please remember to unmute yourself before speaking.
I have a question.
Sure, go ahead.
That was a really nice talk, Lauren. Thanks.
Thank you.
So regarding the conjecture about plane partitions, so the number of plane partitions in a box is also the dimension of a certain nice irreducible representation of a general linear group. I think you get it from taking a homogeneous component of the coordinate ring of a certain Grassmannian as well, actually. Do you see anywhere a general linear group representation lurking behind these tilings?
Oh, that's a good question. I don't know offhand. I don't know offhand. I guess. So you'd want to sort of build a representation with a basis indexed by the pieces of this tiling, I guess.
Yeah.
Yeah. I don't know. It's an interesting question. But offhand, I don't know anything like that.
Are there any other questions or comments?
If I can, I think I have a question, which in a hidden way is somewhat related, maybe. Maybe you can go back to the definition of these twistor coordinates, determinant of y, z in a set I. It's at the very beginning, and sorry about that.
I know. Sorry, I don't know how to do this in a more efficient way. There we go.
So suppose that m is equal to n over 2.
Mm-hmm.
I wonder if it makes sense to define. Actually, this was a kind of a idea that came to me when you have said this. Think about the McMahon boxed plane partition. We all know that there are also the symmetry classes that are often variants of the starting problem. So I wonder if there are symmetry classes of these amplituhedrons. And the simplest case would be when m is equal to n over 2, to ask, on top of positivity and things like that, to ask that you define an evolution on subsets by telling the complement. And you can ask that the twistor coordinate of yzi and of yzi complement are equal. So this is a submanifold in the full set which is somehow related by a symmetry.
Oh,
and I
interesting.
wonder if all of these maybe have a type B analog of this sort, and maybe McMahon plane partitions will be McMahon plane partition in a hexagon with two sides which are equal, which are also symmetric, or things like that.
Yeah, that's a really interesting suggestion. Yeah, yeah, it would be interesting to sort of try to define amplituhedron of type B or whatever. I will say about the conjecture that, let's see. Right, so this is actually not directly addressing your question, but is a bit related. So given that this number m of ABC is symmetric in A, B, and C, then this is suggesting symmetries among tilings of different amplituhedra, right? It suggests that there's a symmetry between k and n minus k minus m, and symmetry between n minus k minus m and m over 2. And the first such symmetry is called parity duality. That was checked by Pasha Galashin and Thomas Lamb. And so that symmetry is known to be true. I think physicists had in some sense known it was true, and then it was proved by them. This other symmetry, nobody really knows. I mean, for one thing, our conjecture could be wrong, but anyway, in the small examples that one can check, it does appear that there is this symmetry between, say, m over 2 and k, or m over 2 and n minus k minus m. But that's an interesting suggestion to look at the subset of the amplituhedron where you have this symmetry among twistor coordinates. Yeah, that's a natural thing to do. Yeah.
So there is a question in the chat, although Sam Hopkins has given an answer, but let's check with you. So Nicola Williams is asking, do you expect that the cardinality of amplituhedron tilings will not be fixed for odd m different from 1?
Yes, for sure, yes. So for cyclic polytopes, you only see, there's a parity thing with cyclic polytopes in odd dimension. I think the cardinalities of their triangulations is not fixed. And so we expect the same to be true for amplituhedra, and already for m equals 1, if I go back to this chart, this cardinality, this n minus 1 choose k, is actually the cardinality of the sort of finest tiling of the m equals 1 amplituhedron, and we can find coarser tilings as well. So so we have a sort of expectation for odd m, but now what you would expect is that this is the corresponding number of plane partitions, and maybe it's like, I forget exactly what it is, but you have to put maybe a lower floor of m over 2 or something. Then this is the should be the cardinality of a finest or like a maximal sized tiling when m is odd.
Thanks, that's very helpful.
Are there any questions or comments? Thank you again.
Thank you.
So we will, so next